extern syllabus. Okay, so the syllabus is there. Your first assignment is to read the syllabus, make sure you know all the expectations, all the guidelines, etc. that are there, all the recommendations. Then on Wednesday, make sure you have got any questions answered, either before then or on Wednesday. Okay? If you haven't had me before, I'm not big on reading things to you. I give you things and expect you to read them. Okay? I'd rather be working problems than trying to teach you things. Okay? I assume you can read, you will read, and you'll be responsible for reading. Yeah? Okay? I don't write things down that are not important. All right? Please read. In the syllabus, those of you who have the organic one, very similar structure, basically identical structure, different content. Back of the second or third page, daily outline. Here. What are we doing today? There we go. Chapter 12, nomenclature, SN1, SN2, E1, E2, overview of alcohols, mostly in review. Lab this week. You either have lab on Thursday or Friday, is that right? Okay. Both days are the same. This is what you're doing in lab. This week, we're checking in, then we'll have the lecture downstairs. Okay, no lab, just check in. All right? So that's the daily outline and the lab schedule. Same textbook as Organic 1, the Klein textbook. Okay, as the syllabus states, you can use any textbook you want. I don't go strictly by a textbook, and also I don't require you to buy a $300 expensive textbook. If you got a $15 or a free textbook from somebody you know, cousin who took organic a couple of years ago or something, it should be very suitable. Please ask. In the end, though, you got to have a textbook, because I'm going to expect that you've done basic reading of the fundamentals of the intro material, working intro problems, and if you're not doing that, you're going to have difficulty with the more advanced type stuff. Okay, you got to get the foundation from the textbook. All right. Now, if you can do well doing some other method, great. I'm telling you the recommended method. All right. And so if you come to me later on having problems, I'll say, where's your textbook? What are you doing in your textbook? Maybe say I'm not doing anything, right? Okay. Then I'm going to say, well, you didn't take my recommendation, and here we are. Okay. The lab techniques book is on the syllabus. The one by Morrig is the one of record. You can use any one. The one by Zubert we used to use. We mentioned a lot of these things on Friday at the pre-course meet and greet, yeah? Also by the email I sent several times. If you haven't gotten my emails, please let me know. Okay? I send you an email with information. Do I expect you to read it? Yes. I'm not going to tell you what was there. Again, I'm not going to waste your time talking to you when I've written something down. Writing it down, you can read it 100 times. If I tell it to you, you go, what did he say? I missed it. What did he say? I'd rather not do that. Okay? Things are written down. I expect you to read them. If anything is ever not clear, please ask. I produced my own workbook, lab manual, just like Organic 1. Here, this can be purchased only in the main office upstairs, chemistry and physics, $15 cash only. It contains worksheets for each test. There will be 4 tests. There is a table of contents. Please look at it. And then the second half of this is the lab manual. So, table of contents for everything there. You got to read the table of contents. I had one student, end of the course, said, oh, I didn't know that was in here. Had the book for 3 months and didn't know that was in here. Okay? I'm like, I recommend you to read the table of contents. Lab manual. Well, what's in there? Well, overview of Organic 2 lab. What's the difference? What are the expectations? Lab safety, notebooks, lab report requirements, checking into and out of lab. Well, we're doing that this week. You need to read that. Those are your instructions and any guidelines. Dr. Stevens, do I need this for lab this week? I'll point you to that section right there. Okay? Because if you're asking me, that means you haven't read that section. Okay, some recommendations there. And in the labs, okay? We're not doing all of these labs. This is my collection of labs that I pull from, like a lab manual. Yeah? Which labs are we doing? Where can you find the labs we're doing? Syllabus, weekly schedule, yes. What's the first lab we're doing? Not this week, but next week. What's that? Okay, it's just a synthesis of phenacetin from acetaminophen. Yes. Is that one in here? It's actually the first one, yeah. The second lab may not be the second one, though. It may be the third or fourth one, yeah? You get started on thinking about lab as soon as possible, yeah? Again, $15, cash only upstairs. I think you'll find this very useful in terms of being organized, okay? Everything there all together. And again, I like to provide lots of clear information and guidelines, okay? And so, I think you'll see that as a valuable resource. Other handouts of the syllabus. One of them was the NMR handout. I sent you this by email. Yeah? But I'm giving you a printed copy. Okay? No extra charge on that. All right? NMR is a big topic, major topic here at the beginning of Organic 2. There was an NMR problem in the pre-course worksheet. But the NMR problems are going to be more than just NMR. They're going to be comprehensive spec problems, including IR, mass spec, and maybe some chemical test information, et cetera, et cetera. Okay. So comprehensive spec problems which you'll see on each test. So we can't forget IR and mass spec, et cetera, for Organic 1. You guys, everybody cover IR and mass spec, Organic 1? Okay. The final exam of this course is the ACS standardized exam, multiple choice, 70 questions, covers both Organic 1 and 2. All right. Basically, read the syllabus, and we can see what other things we need to address on Wednesday or before. One thing you'll see in the syllabus, I recommend writing down your questions and getting them answered. Sometimes students come by office hours and really don't, I had questions, but I forgot. Oh, we'll write them down. Come by and get them answered. Okay? Or I have this question, oh, I had another one I can't remember. Well, write it down. There's also other office hours requirements. A 50-cent composition notebook, good for writing things down, making notes, using it for anything you like. Key thing is to be organized. Okay? Work on being organized. Anybody need a composition notebook. Okay, the other two handouts are for lecture, and we'll get started here. There could be lots of things I could talk about here on day one, but we'll talk as we move along. Again, more on Wednesday probably after things I remember. But I also like to hear from you. What do you need to know? What are your questions? And then I can expand upon things. Any questions, guys? Okay, so again, I have my YouTube page, and we'll be posting the videos for each lecture there. You'll find lectures from the previous 5 years there, including last time I taught this course. They're all by date and topic. Okay, a lot of students look back at older lectures, etc. There's also a collection of videos like for lab techniques like recrystallization, distillation, things like that. There's a few. There'll also be some lecture material covered by video only, where I record videos in my office and post them. And for example, all the nomenclature will be by video only. Okay. Yeah. There'll be a few other topics there, including NMR. NMR I cover by video only. Okay. Because it's a lot of information. It's not overly difficult, but it is pretty comprehensive, a lot of information. Now that's one reason perhaps is because I like to clearly explain it. Okay? I don't just like to say, well, this is it, and tell you in 5 minutes, and then say, okay, everybody understand? No, you can understand in 5 minutes for a full lecture. It takes time to understand it, okay? Ultimately, we got to get down to a point, and I know you guys want to know, what's going to be on the test, right? What do we need to do? Well, we'll get to that point, but there's also just lots of theory behind it if you really want to understand it, okay? And the more you understand it, the more you're going to be able to do well once we start doing the nuts and bolts problems. All right? So, it takes time. I used to cover NMR like about week 3, and then we'd have a test on week 4, and you basically like you'd have a test like a week and a half after you saw NMR. First saw it. You're kind of rushing. So that's one of the reasons I put it on video, so you can have more time. And I sent it to you, several weeks ago. But you can start today, all right? And watch it. Also with videos, you can watch them over and over. You can watch them anytime you want. Watch them in your pajamas, watch them on, whenever. So I think there's lots of benefits to having it by video. The downside is I see some of you guys is you just put it off, and procrastinate. Because, well, you come to class, you have to sit here and listen to me, so you have to go find the videos and watch them. All right? It will be me lecturing just like I would be doing it in class. But again, you can watch them 10 times at your leisure, at your own pace. Okay? NMR. And I will ask you along the way how we're doing with NMR. Any questions on NMR? All right? And when I ask you and you're like, oh, I've never watched the videos, well, then you're behind and things will get worse from there. All right, I will go on and on. Let's see about getting started. Any last questions? So, I hope you have a good semester. Achieve what you want to this semester. Yeah? Everybody got plans, goals for this semester? What you want to... When May comes around, you look back on spring semester, what you have accomplished. All right? I know hopefully you all have plans for this semester, but also beyond. Why are you taking this course? Yeah? It's got to be more than, well, it's required. What are you going to get out of it? My background is in medicinal chemistry, drug development, and I use drug molecules to illustrate lots of the principles. Okay. I know a number of you are interested in health-related, medical-related type stuff. Okay. Drugs are very prevalent there, yeah. Organic chemistry can do a lot for you. We'll talk more along the way. Let's try to get started with some lecture. The green is an outline. I give outlines typically on colored paper. Chemistry of alcohols. Okay. So we'll be referring to that. And then we also have the white handout, Chemistry of Alcohols and Ethers, Warmup. Warmup is sort of some intro, sort of comments, but really some intro problems, okay? Sometimes these will be basic, but most of the time they'll be sort of more advanced, okay? What do we hope to be able to do, you know, after we go through the material and you kind of learn the material that we're presenting here, all right? Sort of stimulate interest. Also applications, okay? Clindamycin is a common antibiotic. Anybody heard of clindamycin? Okay? And so again, see something that hopefully is relevant to you. We can learn some sort of side things, interesting things. Why is organic chemistry important? Okay? Applications. So warm-up is what I call it. Some other faculty use warm-up terminology a little bit differently. Other things here. Okay. Basically, there's lots of questions, lots of places around. You know, actually, I can't remember. I've just recently gone to nomenclature by video only, but I'm not sure I did it for the test 1. Pretty dang sure test 2, 3, and 4 nomenclature is video, but I can't remember if test 1 is. I'm gonna have to check. Because of that, I'm not going to do this if it's there by video. Okay, I'll have to check. But if not, we'll do nomenclature on Wednesday. Okay, or I'll create a video. All right. For this. And we'll move ahead and we'll begin with the next topic here. Basically, our first chapter coverage there is on alcohols and then ethers. And we need to learn how to name alcohols. Now, all your nomenclature is pretty consistent with what you should have seen in Organic 1, right? Longest continuous carbon chain, okay? Then functional group, alkane. If it's got an alkene, we call it an alkene, like propene. What if it's a 3-carbon alkyne? It'd be propyne, right? So we got a prefix with number of carbons. Okay, you know your prefixes, right? And then some type of suffix indicates sort of the main functional group. All right? It's going to be very consistent. All right? Ethanol. What does the F tell you? How many carbons in the chain? 2. And then instead of ethane, we replace the E with OL. The OL is like an alcohol, all. Okay? So it indicates that. Again, but I'm not going to go through this, but I need to see if it's there by video. But we need to know how to name compounds, and then ether nomenclature is there on the second page. And all through my handouts, you will see chances for practice. Okay? There's 3 molecules down here. What do you reckon you should do with those 3? Since it appears on the nomenclature page. Name them? Seems reasonable, right? Okay. Should you try to do those before class as soon as possible? Yeah, because if you work the problems, okay, then you're going to be able to do better. You don't want to come to class and be like, what are we doing today? That's not good, okay? You come to class prepared. You've attempted problems. Okay? If you had trouble with problems, then you're ready to ask questions. Okay? Now, we can't answer every single question in lecture, but maybe you get yours answered. And maybe this person asked the same question that you were anticipating asking, things like that. Okay? All right. Another comment from me. When we come to class, it's showtime. Okay? All right? We come prepared. We come ready for a 50-minute. Okay? If you were doing a performance, you wouldn't show up for the performance and be like, what are we doing today? You would have had a dress rehearsal, you would have had practice, et cetera, et cetera. Then you show up for the performance. Right? Showing up for class is like showing up for the performance. It's go time, it's show time, okay? All right. What's next? Lecture. Okay, I give a combination of outlines and things. The green is sort of a broad overview. Front and back, always, most of the time. And chemistry of alcohols, we're going to begin with substitution. Okay. Then we'll look at, guess what? Okay, so this gives an overview of what we're going to be doing. And then when we get through with alcohols, what might we move on to? Chemistry of ethers and epoxides? Okay. So basically substitution of alcohols, we can replace the OH group, the hydroxyl group, with something, usually a nucleophile, and get a nucleophile on that carbon instead of the OH group. Can an OH be a good leaving group? Yeah. How do you make OH a better leaving group? Typically what? Typically protonated, make it a positive, then it becomes a better leaving group. Okay. Also mentioned, this is largely going to be a review here at the beginning. My handouts, I typically show them and leave room for writing. Okay. Sometimes I don't leave enough room. All right. If you ever have suggestions for, hey, I see there's any more room here, let me know things like that. Okay. I always try to adjust my materials and whatnot. Okay. Substitution reactions. Like we said, OH is a poor leaving group. For rate determining steps, once you have H plus present, you create a better leaving group. Yeah? First example of this, reaction with HX, such as HCl. This will give alkyl halide. Okay? Showing here, if you react this alcohol with HBr, we can get this alkyl bromide. Right? Now, organic 2 is reaction heavy. It's a lot of reactions, largely functional group transformations, converting one type of compound to another. All right? Converting an alcohol to what? Alkyl halide. My handouts try to give very detailed terminology. Okay? You need to read things. What are we doing? Make sure you understand what you're doing before we move on. Okay? And we're doing this right here in bold. Terminology. Alkyl halide. Anybody know what an alkyl halide is? Pretty obvious, hopefully, at this point, yeah? Okay. So, orient yourself to my description of what we're doing. Now we can do it. All right? Well, I already gave you the product here. Told you can do it. Main thing here is, what's the mechanism? What's the first step of this mechanism? What do you want to do first? Well, we've already kind of said it 2 or 3 times. Protonate here. We have lone pair. We have a strong acid. We can just show this ionized. Yeah? Some of you had who for organic one? Dr. Agee? Okay, everybody does things a little bit differently. Hopefully it will be consistent. Okay. These electrons, all right, we can protonate. We got to make the OH a better leaving group. And we get to that there, protonate the alcohol. What's the next step?
Leaving group leaves.
I don't hear well, so whenever you speak, and also need to work on this, whenever you speak, okay, showtime, guys, all right? You're on the stage, I'm on the stage here, all right? You got an audience, I'm your audience. You need to project, okay, loud and proud. You need to stand up, sit up strong, okay? Also, other people need to be able to hear, all right? What's next?
Leaving group leave.
Leaving group leave? To make what? That would be a primary carbocation you're looking for. Primary carbocation's bad, right?
Yeah.
Let's don't form them. Secondary, tertiary, okay. What's next?
Nucleophilic attack.
Reaction can be either SN1 or SN2. Primary OH is always going to be what? SN2, because you don't want to make a primary carbocation. Next step is what? These electrons attack here, kick that off. What does that give? The product plus what? Plus H2O. Yes, there's your complete line reaction. And what's the, what do we call this process here? SN2. Okay? How many steps does an SN2 reaction have? That one has 2. We need, so what?
It has one.
Right. We need to clarify. The substitution part has 1 step, but it had an activation step where we had to activate the leaving group, make it a better leaving group. Okay? I've seen students look at this and say, I thought SN2 only had 1 step, Dr. Stevens. Yes. Leaving group gets replaced with nucleophile in 1 step. SN2. Got an activation step along with it, though. Got to make the leaving group a better leaving group, right? Okay. Does this illustrate what we highlighted up there? Common reaction of alcohols is reaction with HX to make an alkyl halide. This could have been HCl or HI. Typically, HF doesn't work because F- is such a poor nucleophile. Remember, organic 1, we said that. But there's 2 different mechanisms possible. And what if we had stereochemistry in this example? What type of stereochemical outcome do you get with SN2? Inversion. SN2 comes with inversion, like Big Mac comes with fries, right? All right? Next reaction. Take this alcohol, react it with HCl, we can get that product over there. And what's the mechanism here? How do you know it's SN1? Because the potential leaving group, the eventual leaving group is on a tertiary carbon, right? Do we do SN2 on a tertiary carbon? No. How about SN1? Which proceeds by forming what? Carbocation. Is that a good place to make carbocation? Yeah. What do we do first in this mechanism? Protonate it. Can I just protonate it without having to take time? You can't do that on the quiz or test, but I can do it now. Everybody know how to protonate an alcohol? We did it just above. I'm not going to repeat it. Again, on the test, you would need to show that full step. All right. After we protonate it, what's the next step? We got Cl minus, but we don't attack backside and kick off a leaving group on a tertiary carbon. Instead, this just leaves, and what does that do? Carbocation, right? And what's the next step? Now these electrons do what? Bam, right? And what does that do? Product, okay? And what mechanism, overall mechanism was this? Not SN2, but SN1. How many total steps in this mechanism? Total number of elementary steps in this mechanism. 3. Protonate the oxygen. Oxygen ionizes to form carbocation. Nucleophile attacks carbocation, right? What's the rate determining step? Typically carbocation formation, right? There's your product. What type of stereochemistry do you expect to get a product? I started with a chiral product as chiral starting material. What do we expect over there? Because we have a chiral carbon here, right? It's going to be R or S. Be racemic, right? Both. Why both? How do you attack a carbocation? Either side, right? What's hybridization geometry of a carbocation? sp2 trigonal planar. Planar like a piece of paper. Here's the positive. Which side you're going to attack? Either one, 50-50. That's why you end up with racemic. Everybody knows what racemic is? Yeah? Okay. This is optically active. It's a single chiral molecule. That over there is not going to be optically active. Why not? Because it's racemic. Because the enantiomers, the rotation of each individual enantiomer gets canceled out, right? Okay? Some of this review? Hopefully all is, right? Supply mechanism for homework. Supply mechanism for homework. Lucas test. Lucas test can tell you what type of alcohol do I have. That is in terms of primary, secondary, tertiary. Okay, nomenclature we would have pointed out. A primary alcohol is one in which the OH group is on a primary carbon. What type of alcohol is this here?
Tertiary.
Yes, the OH is on a tertiary carbon, tertiary alcohol. Okay, Lucas test can tell you what type, primary, secondary, tertiary you have. Now the Lucas test involves a mixture of ACl, but also zinc chloride. Zinc chloride is a Lewis acid. Which helps make the reaction a little faster. For us, we can pretty much ignore it. What is a Lewis acid? Definition of a Lewis acid, should have learned in Gen Chem. Yeah, accepts a electron pair. Okay. All right. The electrons here, instead of reacting with H+, they can react with the zinc. All right. And basically, depends on how you show this. If you show this as zinc, maybe 1+ and then 1 Cl-, okay? Like partially ionized, you can show this a variety of ways. And then the zinc plus, these electrons here, and you can get to, instead of another H, it's now sort of coordinated to a zinc. But the same thing, the oxygen becomes positive. Okay? Instead of being protonated, it has become zincated or something, whatever. Okay? I've never heard that. Okay? All right? But did it act as a Lewis acid? It accepted the oxygen's lone pair. Okay? A lot of transition metals can do this and act as Lewis acids because they have empty d orbitals. Okay? Transition metals. So it is a Lewis acid, and we'll see Lewis acids along the way, including aluminum. Do we have a periodic table in here? Yes. Okay, transition metals, but also some more main group metals like boron and aluminum we'll see as Lewis acids. In the end, at this point, then you either do SN1 or SN2. The thing with the Lucas test is you got to have some visual observation. And it depends on how fast, how long it takes for a separate layer to form. Now this only works with water-soluble alcohols. You start out with everything in water, including your alcohol. You add in your so-called Lucas reagent, mixed with these called a Lucas reagent, and then shake it, and you see how long it takes to get 2 layers. Okay? The new layer is your product. This soluble in water, do you expect that to be soluble in water? Well, that's an absolute question. Let's ask more of a relative question. Do you expect this to be less soluble in water? Yes, why? Doesn't have as much hydrogen bonding. It has no hydrogen bonding. Okay? The idea of this is soluble in water, and when you do this reaction, it's no longer soluble in water, it's a new compound, and it separates into a second layer. You can see that. Ooh, now I have 2 layers. I must have a new product. That's what it indicates. Okay? Now the Lucas also operates by SN1, because you do it at room temperature. And usually SN2 requires a little heat. Okay? So it is an SN1 mechanism. So what type of alcohol is going to react fastest under SN1?
Tertiary.
Tertiary. We get to the key point, right? Yeah? Because tertiary carbocation is going to form fastest. If you react this with this reagent, it's going to form so fast, the second layer forms very quickly, instantaneously. Secondary is going to take a few minutes, slower. Primary, guess what? It ain't going to happen because you don't make primary carbocations. And so you can keep waiting. You ain't going to get a second layer. All right? So this is going to tell you what type of alcohol you have. All right? Make sense? Any questions? Lucas. Lucas was a chemist, I think, out in California, I believe, back in mid-century. Is his name Howard Johnson Lucas? I can't remember. Howard Johnson hotel, right? No. You never stayed in a Howard Johnson? Holiday Inn? I don't know, somebody can look up Lucas on Wikipedia and tell us his first name. Okay. What's another way to make an OH a better leaving group other than protonating? Tosylate. Convert it to a tosylate, okay? This allows, for one thing, use of stronger nucleophiles, okay? Stronger nucleophiles can be used here. We take alcohol, reacted with tosyl chloride, pyridine, standard base here. We can get the tosylate. I know we covered organic 1. Did you? Other guys do tosylates in organic 1? Okay. And so the oxygen is now bonded to the sulfur, double bonded. Okay. Where do we get the name tosyl? As we'll learn with aromatics, a benzene with a methyl is called toluene. So that's sort of the ta. And an SO2 is called a sulfonyl group. So that's where the S comes from, tos. And the il is sort of just standard endings. So that's a tos. Oxygen here would be O-tos. And an O-tos is a good leading group. Now I put an O in here. TOS, so okay? It's strictly correct to be just TS. Okay? In the textbook, it'll just be TS. Is that how you other guys saw it?
I think you put the O in there.
Put the O in there? Okay, well, it's actually, many people do, but you'll see it just TS in the textbook problem. But it's a good leaving group, okay? It's just as good as maybe bromine or an iodine, okay? Okay? And the OTOS will act as a leaving group on its own.
Where does the hydrogen go?
We'll do the mechanism there, yeah. Once we get the tosylate, then we can come in with a strong nucleophile. Okay? Often an anion, and this will come in here and attack the carbon and kick off the tosylate, the same as coming in here and kicking off the bromine, right? So we can do SN2, kick off the tosylate. And so the nucleophile is now bonded to the third carbon instead of the tosylate. And the tosylate is a leaving group. Yeah? LG, leaving group. Just like maybe bromine or iodine do leaving group. All right? Very common. Why is the tosylate a good leaving group? Well, structure of the tosylate, I mean, it's pretty obvious. It's the same thing there. Now, an aromatic ring is sometimes abbreviated as sort of phi, Greek. So instead of drawing out the full toluene ring, I'm just going to kind of do a short abbreviation to try to save some ink, all right? But you do need to know the full structure of the tosylate group. Okay, why is this a good leaving group? And compared to OH, not a good leaving group for a rate determining step. Good leaving group, why?
The negative charges.
More stable, that's what it kind of implies. Then the question becomes, why is it more stable? It's resonance. There's no resonance here. It's a localized anion. Here you have resonance. These electrons can move in here, and these can move up. And you can, so this charge is delocalized onto this oxygen as well as this oxygen. So it's nicely resonance stabilized. Analogous to sulfate. If under my hand was another O minus, what would that be? It'd be sulfate. And the sulfate is very stable. That's why sulfuric acid is a very strong acid. Right? Instead of another oxygen, it's got the toluene to it. Okay. We'll do mechanism. Before we do mechanism, questions though?
I have a question on the last page when we're looking at that first example with the OH and the HBr. If it was a secondary instead of a primary carbocation, would heat determine whether it was SN1 or SN2? Because H2 is still a good leaving group, so if it's secondary instead of primary.
Well, let's remember what we said in organic one about secondary when we were doing these types of reactions. Secondary can be either.
Right.
Okay.
So would you get both then happening?
Perhaps. Often one will kind of occur. It could depend on fine structure. It could depend on a variety of conditions. If you remember in organic one, we often gave additional information. Maybe you had some rate information to help you decide if it was SN1 or SN2.
Okay.
Remember, sometimes I told you that the nucleophile was involved in the rate determining step.
Yes.
You know,
Okay.
if it's secondary, you're going to need a little bit more information,
Okay.
since it can be either. Primary, you're only going to do SN2. Tertiary, you're only going to do SN1. Secondary can be either. You've got to have a little bit more information supplied. Okay. Such as rate. What if you're doing a mechanism and in the outcome you saw that it was inversion? Obviously the mechanism was
SN2.
SN2. So the inversion kind of told you that, so that the extra information told you it was SN2. Okay, an organic one, I did not do mechanism for making this. Did you guys, Dr. A, did you do it? Perhaps, yeah. I just choose not to do it because it's a little bit different substitution. Basically, the oxygen, what is tosyl chloride? Tosyl chloride is chlorine on the tosyl group. Again, I'll abbreviate. Tosyl chloride. And the oxygen ends up binding to the sulfur instead of the chlorine. Okay? So originally under my hand is chlorine, tosyl chloride. But instead of the chlorine, the oxygen is now bound. And the propyl group is there along with the rod. So it's a substitution, but it's not an SN1 or SN2. It's our very first look at what's called an addition eliminations reaction. All right? And these electrons attack the sulfur. But importantly, we don't kick off the chlorine immediately because we break the weaker bond first. What's a weaker bond? Bond to chlorine, sigma bond to chlorine or pi bond to oxygen?
Pi bond to oxygen.
Pi bond is weaker. We break bond to oxygen. Move those electrons to oxygen. What do we have now? The oxygen now bonded to the sulfur. And electrons went up onto oxygen, and that became minus. We have a double bond to oxygen remaining. We have a bond to chlorine remaining, and we have a bond to the thiamine group remaining. We also have the H here. We don't magically lose H's. And so we just made that bond by a nucleophilic addition. That sulfur is electropositive because it's got 3 electronegative atoms on it, 2 oxygen and a chlorine. All right. At this point, pyridine is a base, and we'll finish up with this. Like benzene, but it's got a nitrogen with a lone pair. It's a weak base. It's included. Eventually, that base is going to take this H. But when? Well, that will also always be the question. And I will say, we got to eventually take care of the proton. We can do it now, we can do it later. I'm going to do it later. The next step is, these electrons then come back down and kick something off. What does it kick off?
Chlorine.
Chlorine. And so that's going to be called elimination. And that gives what are we reforming here? Double bond to O. We had another double bond to O. We had the thiamine group. And is there anything else on that sulfur? No, that's it, right? Still an H here. What did we kick off? We kicked off our LG. When you do substitutions, you replace something. The thing you replace is called the leaving group. Okay? Now, what do we need to do next to get to the final tosylate product? We got to take care of the H. What can take the H? It could be Cl minus. If Cl minus took the H, what would we form? HCl. Typically, you don't like to form strong acid. And so a weak base is included, and it takes the H. And these electrons stay behind, typical acid-base reaction. And what does this give? That gives your tosylate. What else did we form here as byproducts? We formed pyridinium hydrochloride. The pyridine has reacted with that HCl that could have formed. Okay? So instead of forming HCl, which is for practical reasons, don't have time to explain it, just would rather not form HCl in this reaction. Pyridine is often included. The mechanism can be shown a little bit differently. We could have took the proton over here. Once it becomes acidic, you can take it. You'll see slight variations in this. The key thing here is, was it SN1 or SN2? Neither. A brand new type of substitution. Okay? Addition, elimination. We'll do this more and more, particularly when we get to carbonyl chemistry. Okay? Have a good day, guys. We're going a couple minutes over. Addition, elimination, our first look at it. Have a good day. See you Wednesday. Make sure you get the workbook, lab manual.